Okay, let's take a look and see how we would go do this for sampling distribution, not sampling, significance test for a difference in means. So we're going to share screen. Okay, so here's what we got. Many students at math schools claim they think they can think more clearly while listening to their favorite kind of music. Matt thinks music interferes with thinking clearly. To test this, he recruits 84 volunteers and randomly assigns them to two groups. The music group listens to their favorite music while playing a matching memory game. The no music group plays the same game in silence. Below are the summary statistics for the number of turns it takes each subject to complete the game. Fewer turns indicates a better performance. So we got an experiment here because of the magic words. We got assign and we got subject. Those are words that are used in the world of experiments. So that's going to come into play when we do our independent check. So we're running a significance test to see if it increases. So that tells me it's going to be a greater than sign. Our parameters, we have two means. Mu_m is the true mean number of turns when listening to music. Mu_nm is the true mean number of turns when not listening to music. But what we really care about is this one at the end, mu_m minus mu_nm, the true difference in means. We have two hypotheses. We have a null, we have an alternative. The null is always an equal to, and it's almost always going to be equal to 0. It's 0. So mu_n minus mu_nm is 0, that there is no difference. The alternative is we're trying to see if it increases the average number of terms. So the average when we listen to music being greater than the average when we don't listen to music, or another way of thinking about it is that their difference is a positive number. We're going to check our assumptions, random. It states random assign up there. So we're going to go ahead and say we've met that criteria. Independent, since we're dealing with an experiment, we're not going to deal with the 10n rule because this is not a selection with replacement or a selection without replacement. What this is an experiment. We want to say that the results are independent of each other. Basically that the music results have no bearing on the non-music results, and each individual person's has no bearing. That because I'm not listening to music, that has no bearing on whether you're not listening to music and getting a certain number of turns. And then the large enough is really nice because both of these sample sizes exceed 30. Since both of them exceed 30, by the central limit theorem, it's approximately normal. We're going to conduct a 2-sample t-test for true difference in means at alpha equals 0.5. Wasn't given in the problem, so we use alpha equals 0.5. So now we got this formula here in the letters. This thing right here, is not necessary, this piece. I just want to see where I'm getting all these from. What I'm saying is I'm going to take the difference in the two sample means, the difference in the two sample means. I'm going to compare that minus the means, which is up here, that's 0. That's where this two numbers minus 0. And then the standard error down here from the formula sheet is the first standard error squared divided by the sample size, 3.944 squared, divided by 42, 3.550 squared, divided by 42. So now what I'm going to do is pick up my calculator. I'm going to go to stat. I'm going to go to tests, and I'm going to go to number 4, which is a 2-sample t-test. I'm going to use statistics. So what I'm going to do is I'm actually going to put these stats into the calculator. So my first mean, my first standard deviation, the 3.9, my first sample size, 42, my second mean, my second standard deviation, my second sample size. And then this down here is your alternative hypothesis. And again, we're looking at an alternative of a greater than, so we're going to pick the greater than. We never say yes to pool. We're going to go ahead and calculate. And that's going to give me several things. First thing it's going to give me is it's going to give me the t-statistic, 2.59. So that means I can write down this t-statistic, 2.59. Next thing it gives me is the p-value. So what that allows me to do is write down my p-value, 0.0057. The other thing it gives me is it gives me the degrees of freedom. This degrees of freedom, 81.108, that's the degrees of freedom that give me this p-value. So I'm going to write down the degrees of freedom of calculator of 81.108. But what I'm going to say over here is that's what gives me this number. But I'm also going to write down the 2 degrees of freedom of each sample. So remember n minus 1. So in this case, 42 minus 1 is 41. 42 minus 1 is 41. So both of those degrees of freedom. But what I need you to know is this is the degree of freedom that gave me this number. Since our p-value is less than alpha, we reject the null. And then we have that sentence. Since the p-value of 0.057 is less than alpha of 0.05, we reject the null. There is evidence to support the claim that listening to music increases the average number of turns required to finish the memory game. And then the follow-up question is almost always, what kind of potential error did we make? Since we rejected the null, we made a potential type 1 error. What basically I'm saying is that we said that there is an increase. We said that there is a difference when in actuality there would not be. That is a type 1 error. So what we're saying is that listening to music actually makes it take longer to complete this task, when in actuality it really doesn't matter. And the consequence of that is that, you know, Matt decides no music at all, period. Turn off the music, put your iPhones away, put your earbuds away. You can't listen to music because it's going to make you do worse, when in actuality it really has no difference. And that would be a consequence. Maybe you're not as happy in class because you have to deal with that. So that's our test. I want to talk about a follow-up question. This is, again, kind of coming back to some older stuff. Suppose Matt allowed people to choose whether or not they were in the group that listened to music while playing the game. Explain how this might lead to confounding. Okay, here's what confounding is. Confounding is when you have two kind of variables that are in play, and you can't really separate the two. So for example, let's say when I say no music, or I say you get to pick what group you're in, what do you think maybe the no music thing people might have in common? Well, I mean, the people who don't listen to music might also have an increased focus. Like they might have more of a desire. They might have more of a desire to focus on the task at hand. Well, now, what does that mean? Does that mean the fact that they're not listening to music is what made them have less turns? Or is it the fact that they had an increased focus that led to them having less turns? So that's a confounding variable. It's a little more thought process involved in there, kind of thinking beyond, like saying, well, if I allow people to pick what group they're in, what additional kind of things do I have to consider? That's where confounding comes into play. So hopefully that helps. Again, all I ask you to do is practice these. We're doing an activity today where we're going to kind of walk through an example, and then on the back side, there's actually going to be a 2-sample test that I'm going to ask you to work on. I'm going to ask you to just submit that. I can give you comments, give you feedback. Next class, we're going to wrap up with the last topic, and the last topic is a matched pair test. So it's kind of like that interval where we're going to have 2 samples, and what we're going to do with those 2 samples is we're going to figure out the difference between a pair of that sample and run the test on that difference. So it's the mean difference. This was the difference of means, plural. So please always ask if you have questions. Hopefully that helps, and we're almost done with Unit 7.